All right, now as we move into the final part of the summer term here, I have one, maybe two more topics to cover. Uh, in the syllabus, I've labeled them as perception and action and then affordances, but in the PowerPoints that I have, they're both labeled perception and action. And part one is called the standard approach, as you can see here. And we'll make this probably a couple, two or three separate videos. And then part two will be all about affordances. And that one might end up as maybe two different videos as well. So let's get into what we're talking about here. The question is, how do we control our actions? One thing I want to do before I get into the further details about this particular question, I want to situate this material within the class itself, because this might be something that you're thinking, what in the world does this have to do with sensation and perception? Well, as you saw in the title slide, the content is really perception and action. And that's an important phrase, especially with the conjunction and in there, right? Because what I am getting at with that is the idea that the study of perception really is problematic if we ignore action. And therefore, it's important that we include the study of human action, and that means actions, movement, right? How we move our bodies. That requires perceptual information. And that's one thing to say, okay, we should study action and motor control and human movement by incorporating perception, but why do we have to include action in perception? That is, we have to include perception in action, but do we also need to include action in perception? And the answer to that, we're going to learn throughout the course of these notes, is yes, we do need to talk about both of them together. And therefore, any study of perception necessarily includes the study of action. And that's the point of this now, is to understand how we're going to situate study of action into the course. But also, in this unit, we're talking about topics related to how we perceive our bodies, right? And how we perceive our bodies, that is touch or sense of touch, but we're going to go a little further than just using the word touch, is very much bound up with how we move our bodies and control our bodies, right? And I also want to situate this within some of the content that we covered in the previous unit on the ecological approach and the direct perception approach, because this is very much a continuation of that same theme. A lot of Gibson's ideas with regard to perception are also relevant to the ideas we're going to talk about in perception and action, and especially the affordance concept, because just as Gibson gave us the optic array and optic flow and all of that sort of stuff, the affordance concept also comes directly from Gibson's work as well. All right, now let's get into it here. First question, how do we control our actions? Well, the classical approach, as I labeled on the previous title slide there, is known as control theory. And control theory is an engineering term, and we can certainly, well, we're not going to, but we could get into a lot of complex theory and mathematics to understand how control systems work. But we're just going to keep it at the simplest surface level here and talk about the two different types of control that are generally proposed, which are labeled there: feedback control and feed-forward control. You can see also that feedback control is also called closed loop control, and feed-forward control is also known as open loop control. So let me first define them. I also have a little flow chart of sorts on the next slide that we can use as a guideline. And maybe we'll do it this way. This is kind of flipped. I just pulled this picture from somewhere, and they put open loop feed forward on the top and closed loop or feedback on the bottom. So let's put let's start with the feedback or closed loop control, because this is one I think makes some degree of sense, right? So let's come back to our previous slide. Let's talk about using this form of control to control a reaching movement, which that's a simple movement that we do all the time, right? So I'm going to begin by executing the reach, and that means, of course, I'm going to start the movement, and my hand is going to start moving towards a target. But according to the principle of feedback, what's happening is that as the reach movement is happening, I am continuously engaging in some sort of monitoring, and that means perceptual monitoring of the reach movement, right? So what I have to do is I have to continuously evaluate, am I on the right trajectory? Am I on the right path to achieve my target, right? I'm reaching for something, maybe going to reach to pick up a cup of coffee. So the idea is I need to ensure that my hand is always closing the gap, right? That I'm heading in the right direction. So there might be some kind of directional element to our accuracy that I need to be concerned about. But I also need to make sure that I'm closing the gap distance wise and that I'm getting closer and closer to the target, not further from the target, right? So I need to be concerned about both that kind of distance and directional error that might be present. And of course, there always is some error in the sense that in the course of completing the reach, I am not yet to the target. So I might be asking a question as I'm reaching towards the target, not explicitly, obviously, but at some low level, my brain might be asking questions like, uh, am I getting closer? Am I done? No. Am I done? No. Am I done? No, right? It's like the brain is always in this constant state of, are we there yet? Are we there yet? And the driver, the parent who's driving the car, who has to answer this question is always saying no, 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 right? But we are getting closer and closer in theory, right? And and so that's the idea, is that at some point the answer to that question will be yes, we're there, and then we can stop the reach. So let's look at that on the bottom of this flow chart. We have input. So the input is essentially information from the environment of something that I might want to reach for. So visually, I can see the coffee cup on the table. The controller then needs to figure out how to perform the appropriate movement. So that means that maybe I now have to talk about motor control areas in the brain, primary motor cortex and the frontal lobe, as well as premotor areas and all kinds of neuroscience we're not going to worry about here. But that has to generate the appropriate signal. And that signal would take the form of neural commands that descend from the brain to the musculature, right? To the relevant muscles that that need to contract and get the arm going in the right direction. And that starts our process, right? And the process is now the limb is moving. And now what happens is that the goal, of course, is to achieve a certain output, which is to grasp the cup that we're reaching for. But before we get to that, you can see that there's the arrow that's reversing backwards here. And this is where we have our measuring element. And this, of course, now the idea is that what's happening is that some kind of measuring element is comparing the current state of the process with the desired state of the process. And if the desired state of the process is to have my hand wrapped around the coffee cup, but the current state is that I'm not yet there, then the measuring element is going to go back and tell the controller, keep going in that direction. Don't stop yet. Or of course, also, if it detects any sort of deviation that I'm heading in the wrong direction, for example, then the measuring element might say, you need to steer a little bit more to the left or steer a little more to the right. And so this measuring element is continuously detecting the presence of any error, which is I'm not on the right path or trajectory to get to my goal, or I'm not to my goal yet. And that feeds back, hence the name feedback control, as input, as additional input to our controller, which then has to continuously generate new control signals to keep the reach going, right? And eventually, when I get to the coffee cup, Then my measuring element detects that everything is done, which then finally feeds back to the controller to say, all right, everything's done. We're there now, time to stop, right? And then the movement is done. But we kind of go through this looping, and hence the idea of a closed loop, because this completes something of a, it's not really circular in the diagram, but you imagine it as a circle that loops around over and over again until we are complete, right? And that's a feedback system. Now, let's come back here. Feed forward control is known as an open loop. And so an open loop suggests it's almost like an oxymoron in a way, because if it's not really a loop, if it's not closed, right? Or it's not a circle anyway. But the idea here is that nothing loops back really. The system stays open. So what does that mean here? So here I have it in words. We're gonna plan and execute our reaching movement. But then we're not going to correct it. We're just going to execute it all the way from beginning to end. And then once the movement is completed, we can then evaluate, was that accurate or not? Did I reach the coffee cup or not? And if I decided that it was not accurate, my hand landed somewhere else on the table besides the coffee cup, a couple inches to the side, right? Then what I have to do is I have to say, well, I'm going to have to make a second movement now, right? Because now my hand is somewhere else besides the coffee cup, and I'm going to have to plan another second movement to get my hand to that new desired location. And something else might also occur, which is that this information is sort of stored and said, that first movement was inaccurate. So for future purposes, maybe it would be useful for me to evaluate why that movement was inaccurate, so that next time when I'm in a similar situation and I have to reach for a coffee cup in a specific location, I'm going to adjust my movement accordingly, right? So in that case, I'm gradually learning over time. I'm not gradually improving the movement sort of on the fly as with feedback control, but I'm improving my movements after the fact, right? So after I make an error, I learn from that error and I make a modification to how I perform the movement later, right? So let's look at that. This is the top of the diagram here, the open loop system. Again, I have my input, which is the awareness of what's happening in my environment, something I want to reach for. The controller generates the signals that control the musculature, and the movement is then performed. And you see there is no feedback there's no measuring element that detects error and loops back, right? But what is missing here is part of what I had just described, which is that this kind of system, presumably happening in the controller, could learn from its mistakes, right? So after the output is achieved, if we have to determine that our reach was correct or not correct. And then in future situations, the controller might make some adjustments to how it performs its computations that are needed for the control signal. I'm going to jump ahead for a second because let's think about that for a second, right? There's this cartoon I've got, a comic, sorry. So these guys have their pizza cannon, right? And their pizza place is called Ballistic Pizza. So their whole approach here is they get somebody orders pizza. The Johnsons ordered pizza, and their address is 137 Maple Street, right? So what do? They stick the pizza in the cannon, and one of these guys has a piece of paper, and you can see that his piece of paper tells him that for the street address of 137 Maple, that there's some coordinate setting on the cannon that is 849279006, whatever that is, right? But the idea is that you set the control knob on the cannon to that particular number, and that should hit 137 Maple. It's going to land on their front doorstep, and then there you have it, right? Well, how did they get that coordinate 849279006 in the first place? Well, it could be, and one way to do this is You set up your pizza cannon, you look at a map and you figure out where 137 Maple is relative to where your pizza cannon is. You kind of get it pointed roughly in the right direction. And then you shoot your pizza at the house. And then obviously you're probably going to miss. And maybe it goes a little too far, or maybe you've gone a little to the left. So then you come back and you make it the appropriate adjustments to the control of your cannon so that now you're going to aim a little to the right and maybe not quite so far. You change the angles and then you try again. And maybe you got a little closer, but not quite all the way. So you have to go back and you make a further adjustment, right? And you do this over and over again until finally you can get this pizza cannon to land right on the doorstep of 137 Maple. And then you write down those appropriate settings. And you have to do this for every address in your delivery area, right? But once you do this, you have now successfully learned the appropriate setting, right? So the control dial on the side of the pizza cannon is the controller in the flow flow chart that we were looking at for open loop control, right? And the idea is that the input is knowing you have to go to 137 Maple. The controller is setting it at the appropriate setting at the cannon, and then you shoot it, and that's your process, is to just, the thing is launched, and then you observe whether you're right or wrong, right? And the idea is that maybe your first try, you won't be accurate, but on your second try, you'll be more accurate, and on your third try, you'll even be more accurate, and so on and so forth. Notice, of course, that this is called ballistic pizza because, of course, it's equivalent to a ballistic missile or a ballistic bomb that cannot be changed in terms of its trajectory after you launch it. The opposite of that is called a guided missile, which, of course, can be continuously steered all the way to its target. So a better competitor to our ballistic pizza guys would be our guided missile pizza guys if they were to open up next door, right? It's no coincidence, by the way, that the open loop or feed forward system for motor control is oftentimes referred to as ballistic control, because the idea is that the arm is treated like a ballistic missile in the sense that I just kind of shoot it out there and I hope that it's right. Now, this sounds a little strange, right? Because we don't normally execute movements like this, right? I don't reach for an object and miss it wildly and have to try to think about how I'm going to do better next time. Well, except maybe we do, because if you think about infancy, this could be what's happening, right? So this is maybe a decent way to talk about how skill is acquired in our early lives in infancy and early childhood, that infants don't really have good control over their arms, right? And when they reach for something, they're all over the place and they miss pretty badly. But over time, they just get better and better and better. And that could suggest that what's happening is some sort of fine tuning of the control signal in the motor areas of the brain, just like what would be happening with the pizza cannon. We're figuring out the appropriate settings, right? And that's what's happening. There's some equivalent to that piece of paper the guy was holding in the motor area of the brain that fine tunes everything and figures out the appropriate muscle commands needed to do specific kinds of actions. So that has a certain appeal, actually, as it turns out. The idea is that maybe what happens is that we just get so good at controlling movements in our early childhood that we can just develop what's called a motor plan or a motor program that is stored in the brain that basically says, when faced with this particular situation, I know exactly how to aim my arm. So that's a program is really thought to be a set of stored motor commands that I just pull out and execute and say, okay, boom, boom, boom. I can execute my movement exactly as I desired because I am in complete control of everything. I've learned how to do it, right? And that's how I get better. It's also the case, by the way, that sometimes this could make a lot of sense for situations where we really don't have a lot of feedback control. Like imagine if you're in sports, if you're throwing a baseball to another person, you're gonna perform your movement and you're gonna release the ball, and you're not gonna know if you were accurate until you see where the ball lands. And then you have to think, well, I got to do better next time. And so you end up changing how you perform the movement, right? And over time, you gradually fine tune your throwing motion until you can throw accurately. And the same goes for, say, basketball. If you are having to practice doing a jump shot or free throws, again, you can't control what happens to the ball after you release it. So you have to get everything just right in terms of your shooting motion and your release. And then hopefully once that's all set, you practice it over and over again, your motor program potentially has gotten better and better. And you're finally then able to accurately hit a jump shot or a free throw, right? But we might also say that there might be some situations where maybe we do use feedback control. Maybe it's not all feed forward, because if you think about another situation where you are reaching to pick up, let's say you're having lunch in a fancy restaurant, right? A formal dinner, and there's a tiny little delicate teacup on the table, and last thing you want to do is spill it. So as you reach to pick up the teacup, or break it even, you don't want to do that. So as you reach for it, you have to be really careful. So you're going very slow. You don't want to knock anything over. And so you're paying very, very close attention to what your hand is doing the entire time. And so in that situation, maybe it sounds like you're definitely using feedback control to ensure the highest level of care and precision in your movement, right? And so we might think, well, we might have a situation here where sometimes, as it happens in science, you can see there could be a debate where some people might want to argue that motor control and human action is achieved via feedback systems always, and other people would say that no, skilled movement is achieved via feed forward open loop control always. But maybe it's the answer somewhere in between, that it's both, right? And that maybe there's situations where we use open loop control, and there are situations where we use feedback control, right? But in order to understand how we can explore this further, and importantly, incorporate the role of perception, we need to ask another question, which is, what is the information, that is perceptual information, that these two types of control systems require? So we talked about input, right? And I said before that input in the flow chart there is some kind of perceptual information that would be needed by the controller to generate the appropriate motor commands. But as it turns out, it might be the case that the kind of information that these two systems need would be very different from each other. So let's look at feedback control. So when I'm reaching towards the object with feedback, do I need to know exactly how far away it is? Right. So if an object is, let's say, 50 centimeters away from me, then that could be useful information, right? But if my hand is approaching the object and I'm getting closer and closer to it, do I really need to know that that object happens to be 50 centimeters away from my hand, and then after another second goes by, it's 48 centimeters away from my hand, and so on and so forth, so that I always know the exact distance? Well, the answer to that is no. According to feedback control, we don't really need to know anything about the exact, definite, precise distance or direction of the object. What I really need, maybe that information is useful at the beginning of the reach to get my hand going at the right speed and the right direction. But as the reach is unfolding, I really only need information about the relative spacing between my hand and the object, right? I need to know what's the is the distance or the gap, I might say, between my hand and the object, is it shrinking? And so that just means that my hand's getting closer to the object. It doesn't matter if I know exactly how far away it is. I just need to know that I'm getting closer, closer, and closer versus farther and further. Because if it's further and further, then that would be feedback information to tell me to adjust my movement to go some other direction, right? So I need this information about just relative spatial information. You know, what's the relative distance between my hand and the thing I'm reaching for? Having some temporal information would be useful because this may depend on how fast you're going, right? The idea is that if you're going really, really slowly, this means you've got lots of time and you can take your time to make small corrections to the movement. But if my hand is traveling quickly, that gives me less time to make small adjustments to my movement. So maybe I can't really make too many rapid adjustments to a reaching movement if I'm trying to reach very, very quickly to something. So knowing something about how much time I have left before I hit this object I'm reaching for would also be useful. So I want spatial information, I want temporal information about how the reach is unfolding. But importantly, I just need relative spatial information, right? But note here, feed forward control seems to require something else. It requires absolute information, right? So if I'm reaching for something and I don't know how far away it is, how am I going to pre-plan that movement appropriately, right? This is exactly what I was getting at maybe with the pizza cannon over here. Our pizza guys know that the address for the Johnsons is at 137 Maple. So that's an absolute spatial address, right? They know where in the neighborhood 137 Maple is. So they know exactly where they have to go in a spatial coordinate setting. Presumably they have a map of their delivery area. And that map tells them exactly where things are in some spatial system that is defined by street names and house numbers, right? And they know how to convert that information into the appropriate angular settings on their pizza cannon, right? So the same would have to apply for feed forward control. What we have to have is we have to have a complete spatial map of the environment around us. But instead of the pizza delivery area, it would be something more about our reach area, right? How far can presumably that pizza cannon can only go a certain distance. And likewise here, my arms can only travel a certain distance. And so I have to have some sort of a very accurate spatial mapping of the world around me, at least in sort of what we might call peripersonal space or reach space. And I need to know exactly where everything is within that space. And then I have to have that coding scheme that converts positions in the reach space or peripersonal space into limb space or limb coordinates, arm coordinates, hand coordinates, something like that, right? So what I do is once I know where my hand is in the space and I know where the object is in the space, this is when I have to compute an appropriate trajectory, right? And the trajectory then is that pre-planned or pre-programmed reaching movement. So knowing that my hand is at position A and my target is at position B means that there's going to be a certain kind of trajectory that my hand needs to follow to go from point A to point B. And I have to be able to plan that all in advance by having the brain calculate the appropriate muscle contractions to make my hand do exactly that, right? So it's the equivalent of adjusting the pizza cannon, right? But one of the things that I just said, let me run back here real quick, is that not only do I need to know where the object is in this space around me, but I also need to know where my hand is in the space around me. Now, asking the question and answering the question of how do I know where the object is in the space around me is a topic that's already covered, right? We've covered that in the size and distance perception content. And that chapter in particular, we're talking about depth. And it also is relevant a little bit for optic array and optic flow stuff too. But one question we haven't yet addressed, and this is where we need to go next, of course, is how do I know where my hand is in that space? And that seems again like, well, don't we just know? Well, obviously, no, we don't just know where our hands are. All right. There has to be a source of information for that. And that's going to be something I will then save for our next break. Break. I'll give it a break here, and in the next video, we'll talk more about how do we solve or figure out the answer to this question.